All right, let's take a trip way back in time. I mean, way, way back to the dawn of computing. We're going to explore a really simple question. Before we had Windows or Mac OS, how in the world did the very first giant computers get any work done at all?
I mean, seriously, think about it. Before you had a supercomputer sitting in your pocket, how did anyone actually compute anything? It's a world that feels, well, it feels almost alien to us now. So let's set the scene.
We're talking about the 1960s. And when we say computers, don't picture a laptop. Picture colossal machines. I mean, behemoths that filled entire climate-controlled rooms. They were incredibly rare, unbelievably expensive, and built to solve only the biggest problems of the day. So who even got to use these things? Well, not you and me. Access was hyper-exclusive. We're talking about massive organizations like NASA, major research labs, basically any institution that had computational problems so huge they just couldn't be solved by hand. Okay, and here's where we get to the single biggest difference between then and now. You couldn't just, walk up to the computer and use it. Nope. To get anything done, you had to go through a person, the operator. They were the human gateway to the machine. So let's meet the main players in this whole drama. First, you've got the user, a scientist, an engineer, someone with a big problem to solve. Their program wasn't a file on a disk. It was a physical thing called a job, encoded on a stack of punch cards. Then you've got the room-sized computer itself, and holding it all together, the most critical piece of the puzzle, the operator.
And you really have to let this sink in. The operator was, for all intents and purposes, the original operating system. Literally, they were a human interface. They physically collected programs, decided what to run and when, and managed the machine's entire workflow. You didn't talk to the computer, you talked to the operator.
So what did this look like in practice? Let's actually follow a single job on its long physical journey from a stack of paper cards all the way into the computer's electronic brain. So it all started with a user, maybe a physicist, handing their stack of punch cards to the operator. Now, the operator wouldn't just run it. Oh no. They'd collect jobs from a bunch of different users, and, here's the key part, they'd sort them into groups of similar tasks. This group was called a batch. Only then would they feed that first batch into the machine, and the computer would finally get to work on the first job. And that, right there, is where the name batch operating system comes from. The entire philosophy was built around this idea of batching. See, by grouping similar jobs together, the operator could make things more efficient, minimizing all the manual setup and configuration that had to happen between different types of programs. It was all about streamlining. Now, on the surface, this all sounds pretty logical, right? A decent first attempt at organizing a workflow. But this system had a gigantic hidden flaw, a flaw that was costing these organizations a fortune in wasted potential. So, picture it. Batch number 1 is loaded up. The first job is running. That multi-million-dollar CPU is just blazing through calculations at a speed that was absolutely mind-blowing for the 1960s. Everything is humming along perfectly. But then, bam! The program hits a line of code that needs to do something physical, something slow. It's called an I/O operation, input/output. Maybe it needs to read some data from a clunky, slow-moving magnetic tape. So what does that incredibly powerful, incredibly expensive CPU do while it waits for that mechanical tape to spin up? The answer is kind of shocking. It does absolutely nothing. The CPU just stops, its state becomes idle, and all that amazing processing power just sits there, completely wasted. And this right here shows you the core problem in a nutshell. That CPU would not move on to the next job in the batch. It was stuck, just waiting for job number 1 to finish its slow I/O task. Today, your computer CPU would instantly switch to another 100 tasks in that same amount of time to stay busy. But back then, all that precious processing power just vanished. So imagine what this meant for the poor user who submitted that job. This quote really says it all. You don't know when you will get the result. Maybe you'll get the result after a day or a week or a month or a year. The turnaround time was a total mystery, and often it was an agonizingly long wait. Yeah, a system where your most expensive component sits around doing nothing most of the time, that just wasn't going to fly for long. This massive inefficiency was the exact thing that lit a fire under everyone to innovate and build the next generation of operating systems. So things had to change. The first step was the arrival of monitors. Not screens, but early software that started to automate parts of the operator's job. This was a big deal, and it paved the way for the real revolution, multiprogramming. This was the game-changing idea that the CPU should never be idle. It could just switch to another job while the first one was busy doing something slow.
So if you take one thing away from all this, it's this. For all its logical attempts at organization, the single biggest failure of the batch operating system was the colossal, mind-boggling amount of wasted CPU time. It was a system that, ironically, ended up throttling the very electronic brain it was designed to serve.
Which leaves us with one last really interesting question to chew on. If these batch systems were so slow, so inefficient, and so frustrating, why do we still look back on them as a totally revolutionary and necessary step in the history of computing? Something to think about. Thanks for diving into this with us.